Magnetic phenomena are universal in nature. Vast, distant galaxies, the tiny invisible atoms, men and beasts, all are permeated through and through with a host of magnetic fields from a variety of sources. A thin, long piece of a magnet, when suspended freely, pointed in the north-south direction. A similar effect was observed when it was placed on a piece of cork, which was then allowed to float in still water. The name lodestone, given to a naturally occurring ore of iron magnetite, means leading stone. The bar magnet. In bar magnet, there are two poles. One is north pole and second is south pole. All magnets have their own magnetic field. If any iron particles comes in that field, bar magnet will attract towards itself. The pattern of iron fillings suggests that the magnet has two poles similar to the positive and negative charge of an electric dipole. As mentioned in the introductory section, one pole is designated the north pole and the other the south pole. When suspended freely, these poles point approximately towards the geographic north and south poles respectively. A similar pattern of iron fillings is observed around a current-carrying solenoid. The magnetic field lines. The magnetic field lines are a visual and intuitive realization of the magnetic field. Their properties are: the magnetic field lines of a magnet or a solenoid form continuous closed loops. The tangent to the field line at a given point represents the direction of the net magnetic field B at that point. The larger the number of field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. The magnetic field lines do not intersect, for if they did, the direction of the magnetic field would not be unique at the point of intersection. One can plot the magnetic field lines in a variety of ways. One way is to place a small magnetic compass needle at various positions and note its orientation. This gives us an idea of the magnetic field direction at various points in space. Bar magnet as an equivalent solenoid. The resemblance of magnetic field lines for a bar magnet and a solenoid suggests that a bar magnet may be thought of as a large number of circulating currents in analogy with a solenoid. Cutting a bar magnet in half is like cutting a solenoid. We get two smaller solenoids with weaker magnetic properties. The dipole in a uniform magnetic field. The pattern of iron fillings, that is, the magnetic field lines, gives us an approximate idea of the magnetic field B. We may at times be required to determine the magnitude of B accurately. This is done by placing a small compass needle of known magnetic moment M and moment of inertia I, and allowing it to oscillate in the magnetic field. The electrostatic analog. Magnetic field at large distances due to a bar magnet of magnetic moment M can be obtained from the equation for electric field due to an electric dipole of dipole moment P. Magnetism and Gauss's law. We see that for a closed surface represented by I, the number of lines leaving the surface is equal to the number of lines entering it. This is consistent with the fact that no net charge is enclosed by the surface. The Earth's magnetism. The strength of the Earth's magnetic field varies from place to place on the Earth's surface, its value being of the order 10 to the power minus 5t. What causes the Earth to have a magnetic field is not clear. Originally, the magnetic field was thought of as arising from a giant bar magnet placed approximately along the axis of rotation of the Earth and deep in the interior. The magnetic field is now thought to arise due to electrical currents produced by convective motion of metallic fluids in the outer core of the Earth. This is known as the dynamo effect. The magnetic field lines of the Earth resemble that of a hypothetical magnetic dipole located at the center of the Earth. Magnetic declination and dip. Consider a point on the Earth's surface. At such a point, the direction of the longitude circle determines the geographic north-south direction. The line of longitude towards the North Pole being the direction of true north. The vertical plane containing the longitude circle and the axis of rotation of the Earth is called the geographic meridian. Magnetization and magnetic intensity. The Earth abounds with a bewildering variety of elements and compounds. In addition, we have been synthesizing new alloys, compounds, and even elements. One would like to classify the magnetic properties of these substances. Magnetic properties of materials. The discussion in the previous section helps us to classify materials as diamagnetic, paramagnetic, or ferromagnetic in terms of the susceptibility X. A material is diamagnet if X is negative, para if X is positive and small, and ferro if X is large and positive. Diamagnetism. Magnetism. A bar of diamagnetic material placed in an external magnetic field. The field lines are repelled or expelled, and the field inside the material is reduced. When placed in a non-uniform magnetic field, the bar will tend to move high to low field. In this diamagnetism, Electrons in an atom orbiting around the nucleus possesses orbital angular momentum. Diamagnetic substances are resultant magnetic moment in an atom is zero. When magnetic field is applied, those electrons having orbital magnetic moment in the same direction slow down and those in the opposite direction speed up. Diamagnetic substances are those which have tendency to move from stronger to the weaker part of the external magnetic field. In other words, unlike the way a magnet attracts metal like iron, it would repel a diamagnetic substance. Paramagnetism. Paramagnetic substances are those which get weakly magnetized when placed in an external magnetic field. They have tendency to move from a region to weak magnetic field to strong magnetic field. That is, they get weakly attracted to a magnet. Ferromagnetism. Ferromagnetic substances are those which gets strongly magnetized when placed in an external magnetic field. They have strong tendency to move from a region of weak magnetic field to strong magnetic field. That is, they get strongly attracted to a magnet. Permanent magnets and electromagnets. Substances which at room temperature retain their ferromagnetic property for a long period of time are called permanent magnets. Magnets and electromagnets. When the core of the electromagnets are made of ferromagnetic materials which have high permeability and low retentivity, soft iron is a suitable material for electromagnets. On placing a soft iron core in a solenoid and passing a current, the magnetism of solenoid is increasing by 1000-fold. Then switch off the solenoid current. The magnetism is switched off, but at that time the soft iron has a low retentivity. Thus, at that time the soft iron core in solenoid acts as an electromagnet.